In 2015, a massive earthquake hit Nepal. From above, the destruction looked endless. Entire neighborhoods turned to rubble and dust in seconds. Streets that were once full of life became cracked concrete and twisted metal. Homes crumbled. Chaos reigned. But not everywhere. Just like a sandcastle washed away by waves, most buildings couldn't withstand the force. But what if some were built to ride the waves instead of fight them? Engineers around the world have cracked a new kind of architecture, buildings that flex, sway, and absorb shock instead of collapsing. Same street, same soil, same shaking, one side destroyed, the other still standing. So, what made the difference? The answer lies in a principle you already know, like your car's suspension, absorbing every bump in the road, softening the ride to keep you steady. Engineers took that same idea and scaled it up, using models, simulations, and wild inventions to make buildings that bounce, not break. Now, some of the world's most advanced cities are filled with these earthquake-ready giants, silent guardians, made of steel, science, and smart design. You're watching engineering intelligence. And this is how we build cities that survive earthquakes. So, what made the difference between collapse and survival? The secret lies in how a structure moves when the ground no longer does. Earthquakes give you no time to think. They hit in seconds, with forces stronger than steel. No early warning system can save a building that wasn't ready. So how do you build something tall enough to defy gravity, but flexible enough to survive motion from below? That contradiction is the engineer's nightmare. And for decades, we failed to solve it. Rigid towers snapped like twigs. Massive beams bent and tore under their own weight. Cities collapsed again and again until new ideas emerged, ideas borrowed from the world around us. From suspension bridges to bamboo stalks to the simple balance tricks in children's toys. These breakthroughs didn't fight the quake. They flowed with it. The best buildings today are designed to work with the shaking. They sway, they slide, they survive. So how exactly do you earthquake-proof a building? One of the most powerful tools against earthquakes is isolation. Not by fighting the shaking, but by escaping it. Engineers found strength in controlled motion, not force. What if a building didn't resist the quake, but moved with it? That's the concept behind base isolation. Base isolators are like giant shock absorbers beneath the structure. Rubber bearings, sliding plates, they absorb motion before it hits the building. Without isolators, buildings sway and crack. With them, that violent energy gets stretched out, like landing on a cushion. Imagine standing on a skateboard during a quake. You still move, but it's smoother. That's what base isolation does for buildings. It's not futuristic. You already use it every day. Your car's suspension isolates you from bumps. Same idea, bigger scale. Today, base isolation protects buildings worldwide, from hospitals in California to airports in Istanbul. Built to ride the quake, not resist it. What if the secret to keeping a skyscraper safe is letting it sway? It sounds bizarre, but sometimes movement is the best defense. In a tall building, the top floors act like the tip of a diving board during an earthquake, swinging wildly with every shake. That kind of motion isn't just scary, it's dangerous. So engineers came up with a counterintuitive idea. What if you hang a massive weight inside the building and let it swing in the opposite direction? It's called a tuned mass damper, and it works like a shock absorber for skyscrapers. When the building sways one way, the damper pulls the other, canceling out the movement. You've actually seen this principle before. Ever carried a full tray of water? You instinctively shift your arms to steady it. That's a tuned mass damper. One of the most famous examples? Taipei 101, a 1,600-foot skyscraper in Taiwan. Near the top, there's a 660-ton golden sphere that swings. It's suspended by thick steel cables, and during earthquakes or typhoons, you can actually watch it move, silently protecting the entire building. The damper doesn't stop the shaking. It dances with it, absorbing, balancing, countering. It's motion, fighting motion. That's the magic of earthquake engineering, not resisting nature, but working with it. And sometimes, survival means letting go. Just enough. Try snapping a dry stick. Easy, right? But now bend a blade of grass. It flexes, survives. Buildings, just like plants, need to bend, or they break. Modern engineering stopped trying to fight the force of an earthquake and started learning how to flow with it. That shift changed everything. One key: reinforced concrete, infused with steel rebar. The concrete takes the pressure, the steel handles the stretch. Together they flex instead of snap. Next, shear walls. These vertical cores act like internal spines. They spread out seismic forces, so no one part takes the hit alone. Then there's cross-bracing, diagonal beams that stop walls from folding. It's a bit like tying shoelaces tight, keeps everything in place. Buildings are also designed with balance in mind. Engineers align the center of mass and stiffness, like balancing a pencil on your finger. Take Tokyo's Midtown Tower, steel skeleton, shear walls, flexible joints. In the 2011 quake, it rocked, but it stood. It's not unlike a palm tree in a hurricane. It bends wildly, but it never breaks. That's flexibility as strength. Earthquake proofing isn't just about high-tech tricks. It's about building smarter, from the ground up. It's easy to say a building will survive an earthquake, but engineers can't work on guesswork. They need evidence, hard, tested, repeatable proof. That's why engineers go to extreme lengths, recreating earthquakes before they happen. Inside massive labs, they simulate destruction, under total control. They use giant shake tables, enormous platforms that jerk and jolt with precision. Some are the size of a tennis court and can mimic earthquakes from anywhere on Earth. Engineers build detailed scale models of real skyscrapers, then violently shake them. It looks like destruction, but it's actually progress. Some models stand tall, others snap, tilt, or crumble. And every failure is a goldmine, revealing weak points before they go into real buildings. Dozens of motion sensors track every wobble. Strain gauges detect stress inside the walls. High-speed cameras record each collapse, frame by frame. All that data goes back to the drawing board. Designs improve, materials get smarter, cities become safer, one experiment at a time. These aren't just experiments, they're rehearsals for survival. Every bolt, beam, and blueprint is backed by data, not hope. Because when the ground starts shaking, it's not bold claims that save lives, it's proof. Think this is just for engineers in labs? Think again. With just a few everyday items, you can build 3 of your very own earthquake experiments. We've created 3 simple DIY demos that show how base isolation works in real time. You'll get a step-by-step guide, full material list, and clear illustrations, all in a downloadable PDF. It's perfect for classrooms, STEM activities, or just a curious weekend. Grab your copy now, link below, and test your tower against the shake. Earthquakes are unstoppable, but the collapse of cities doesn't have to be. It all comes down to one thing: smarter engineering. From base isolators to mass dampers, from flexible steel to clever design, every breakthrough starts with a question: how can we do better? You've been watching Engineering Intelligence. If you learned something new, subscribe for more. We've got a lot more to explore.